So my name is Michael Way. You can call me Mike. I and Kostas Sigouridis, who's sitting to my left, and Igor Alienov, who just came in, will be running this tutorial. So if you have questions, please address them to us. Sometimes I'll be driving, sometimes Kostas will be driving, sometimes Igor will be driving. And tomorrow morning, our colleague Tom Clooney down at Goddard Space Flight Center will be talking to us about what we call the calendar in the model, which is basically how we change rotation rate and things of that nature, orbital parameters in the model, which is quite complicated, and he's the one that put that implementation together. We are recording this session. Last year we did record our sessions, and all of those are up on this link to YouTube here, as you can find. Hopefully we'll do a better job of recording this year than last year. We'll see how that goes. So if you have colleagues that want to use the model, hopefully if they can't make it, they can look at these YouTube links about how to get things going. Anything else we should say, Kostas?
No, I don't think so.
No? Okay. We're going to go for about an hour, and then we'll take a break. We're not going to make people sit for 2 or 3 hours at a time. I don't think that's very conducive to learning, having gone to school way too long, like most of you, from experience. So we'll have a break in about an hour from now, and then we'll continue until around 12:30, as we have in the schedule here. Break for an hour and a half for lunch, and then we'll pick up in the afternoon. We'll mostly be doing Q&A, seeing what you don't understand about what we already talked about. If there's any questions you have, we will take them and see how it goes. As I said before, please make sure your microphones are muted. Local people should make sure the telephones are muted. Kostas is monitoring the chat window, so if you want to bring something up, you can chat with him there, and we'll bring it up here if necessary. Otherwise, you can try to pick up the microphone and see how that goes. Okay, so we'll start very basic here. I'm not going to go into a lot of details about what a 3D GCM is. I assume that you're here because you know what a 3D GCM is. But our model itself works on a lat-long grid. Presently, we have our model is the child of a parent Earth model. So we have a lot of legacy from the Earth model, which gives the model a lot of features. But a lot of those features, of course, are coded for Earth in the sense that we have certain temperature regimes we expect and things of that nature. And if we go outside those bounds, often the model will complain or even crash, saying you have gone outside the bounds of what we think the physics can do in this model. Sometimes the model will just keep on running though, and you'll be outside the bounds of physics and you won't know it. So you have to be very careful with these models in understanding what you might expect them to produce. Don't expect the model's going to give you the right answers just because you think you put everything in correctly. It's not a winning formula for a successful science project, I would say. So I thought we'd mention a few limitations of the ROCKE-3D GCM as it stands today. The timescales of the model. So we do not do geological timescales, of course. We've done maximum length simulations with the 4x5 20-layer version of the model. What I mean by that is the 4x5 lat-long grid, which we use by the default in the current version of the model, which we call Planet 1.0. And the 20-layer version of the atmosphere, the default number of layers is 40, which we have done a simulation that reached, well, I guess around 8,000 years. That took about 4 months. Depends on, the contention on the computer, how fast your processors are, and things of that nature. But you can think of the maximum time you can go is around 10,000 years within reason, unless you want to run for a few years on wall clock time. Vertical range goes in the atmosphere up to about 65 kilometers. We cannot simulate atmospheric escape with this model. And we only have mixing ratios up into the stratosphere for the atmospheric constituents. we're limited to shallow atmospheres in our GCM. We cannot do mini Neptunes. We cannot do modern day Venus, things of that nature. And the same applies to the ocean. The ocean is really what we would call a thin atmosphere approximation. We do go down to 5,000 meters, but we do not go into the kilometer range. Although we do have we did recently get some one-year pilot money to try to expand the model to do ocean waters, like we are found on Enceladus and Europa. But that's a work in progress. A lot of physics has to be redone, and some other adjustments have to be done. Yes, Daniel?
The shallowness just means primitive equations, or is there extra approximations beyond the primitive equations?
I don't know the answer to that exactly. Yeah, I'm
Okay.
sorry.
Yeah,
Maybe Tony could.
Yeah, so there's a variety of things, right, that depending on the planet that you want to do, that we can't do with ROCKE-3D. So we can't go to a very deep atmosphere, okay, so we don't include those higher order Coriolis terms and things like that require the shallow.
But people have done like the weather layer of Jupiter in a GCM. Like this would,
But not in this GCM.
Not in this GCM, right? Okay, and then also, maybe you'll get to this later, we can't do the types of things that, let's say, Ding and Pierre Humbert are doing with atmospheres where water is a substantial fraction, but variable of the atmosphere, because this does not track water. The dynamics does not track water mass, and so we have to keep below ranges where water becomes a significant fraction of the atmosphere. We currently don't have high temperature line lists in there, although that's something that can be fixed, so we don't go about 400K, and maybe you're going to go through these.
Yeah, we'll talk about a few of those things. So.
yeah.
Yeah, 10% is pretty much the max. The person giving the answer for those online is Tony Del Genio, the leader of the Nexus project here at NASA GIS. So you'll hear Tony probably chime in a few times during the tutorial. So those are some of the limitations. The ocean tends to run at 32 layers, although you can run shallower layers if so desired for a given planet. This is kind of an abstract picture of what the Earth climate model looks like, which we, as I said, are a child of. This is from Gavin Schmidt's paper in 2017. I'm not going to go into any depth here, but you can see where the atmosphere and the chemistry are coupled to the ocean model and the land model and the vegetation model and the land ice model and the sea ice model, et cetera, et cetera. So it's very complex. Yes, that was a local person turning on their microphone. Okay, so I thought we would just give a little summary about what ROCKE-3D is good for. For those of you that don't know, that we do have a model description paper. If you want to know about the basics of the model, this paper tries to describe it, and there's a lot of references to the Earth parent model, which you can dig into. But I thought I'd just give a few examples of what this model has what we believe successfully has modeled in the past. We have done some Archean Earth type simulations, some of which was published in a book chapter that Tony Del Genio led this previous year. These are some simulations from that book chapter from the Archean at around 3 gigayears ago. Although we have gone back as far as 4.2 gigayears ago, we have the correct solar spectrum back to 3.8 gigayears ago. And of course, you can adjust how much solar insolation you want for your world in the model without any problem. We have done some simulations of a hypothetical ancient Venus at the inner edge of the habitable zone, which is a fairly well-known work, where we use solar installations from the appropriate time periods and slow rotation rates, things of that nature, and of course using normal Earth atmosphere constituents for today. We have done some simulations for modern and ancient Mars without CO2 clouds, although we have some runs with CO2 condensation involved. This is an example from the ROCKE-3D description paper for a run that Igor Alienov did, comparing the surface pressure over time compared to the Viking 2 data set of 1977. Some hypothetical Venus-like worlds near M dwarfs, unlike our Venus, which is around a G dwarf for Kepler 1649b. This was a paper that was run by Stephen Kane and some simulations we have done here. Most of these simulations did not end up in thermal equilibrium, which we'll talk about a little bit later in the tutorial and what that really means. And then Tony Del Genio led a paper that was took, I guess, about a year and a half to get published, it seems like. Astrobiology took a long time to get this paper published for hypothetical proximatory B-type worlds with a range of different atmospheres and oceans that were done. In this paper, I think it's the only published work we have where we actually used a 10-bar N2 atmosphere. ROCKE-3D does go up to 10-bar atmospheres. We do have the spectral line list for that. And total 10-bar N2 or CO2-dominated 10-bar atmospheres are also permitted. And recently, Igor Lienov led a paper for doing an ancient lunar atmosphere. So we can get down to atmospheres of 1 millibar. And our goal, we just submitted a ROSA's proposal to SSW, try to get down to roughly 10 microbar atmospheres over the long term. So we want to be able to go from roughly 10 microbars all the way up to 10 bars with this model. That's our goal. But in the short term, we have this paper on an ancient lunar atmosphere to a single millibar total atmosphere. This is a CO2-dominated atmosphere in one case. In the other case, it's a CO2-dominated atmosphere. Sorry? CO and CO2, sorry. CO and CO2, different atmospheres. Okay, there are caveats, as I have mentioned a little bit. There's a limited number of types of atmospheres and stellar spectra that are available, and we will discuss those in some detail depending on how much time we have. But for those of you that want to do different kinds of worlds around different kinds of stars, at least at present we have a limited number of stars available and different kind of atmospheres available. But if you become an expert in the model, it's not impossible for you to put your own stellar spectrum into the model and to generate your own spectral files, as we call them, to allow you to different kinds of atmospheres. In fact, that's one of the reasons why we do these tutorials. It's not completely altruistic. Some of it is selfish. We are hoping that some of you will eventually get involved in the model at the development level and contribute code to the model to help us all bring this community model to a larger group of people around the world.
Mike, is that another case where it's a bit of buyer beware when you start doing that? Because if you introduce a stealth spectrum that may result in a large amount of infrared flux that would change the physics of what ROCKE-3D is expecting, could it lead to?
Well, it's something, I mean, as always, like I said in the beginning, anytime you change something in the model, you have to be cautious of what you see come out of the model. I would say that in general, though, the stellar spectrum should not be a big issue, changing that, because we have done we've done a number of different M-dwarf stars that are
TRAPPIST, right?
We've done TRAPPIST and we've done Proxima Centauri B, and we have a few others. We have some K-dwarf spectrum in the database, and we have a range of, I think we even have an F-dwarf now. So at least in our own tests, I would say that the results look fine from our perspective. So
can I just maybe
yes, please tell me, go ahead.
Something to Stephen's question, and that is that the stellar spectrum that you use is not independent of the rest of the radiation. So the way we wound up doing things when David Amundsen was here was to create spectral files for specific atmosphere star combinations. Okay, and so it's not just a matter of taking the existing spectral files and just sticking another stellar spectrum in. Eric, who knows the radiation now more deeply than I ever have, can correct me. I didn't say anything wrong, but basically we were trying to make sure that the radiative fluxes and heating rates were sufficiently accurate for any atmosphere that we did, so that we didn't have to worry too much about that part of the model. And so David adopted this philosophy of creating spectral files, not just for a particular atmosphere. You want to do, a 10-bar CO2 atmosphere or something like that, but a 10-bar CO2 atmosphere illuminated by a TRAPPIST spectrum versus 10-bar CO2 CO2 atmosphere illuminated by the sun are two different spectral files. And so it's the atmosphere star combination that has to be specified. So if you stick a new star in, it's very different from the one for the spectral file that you're using, and you probably have to switch to a different spectral file, or maybe create new ones that are appropriate to that.
Yeah, the only thing I would add is that in the making the shortwave spectral file, the absorption coefficient, there's a step where to increase accuracy, the solar spectrum is weighted into the absorption coefficient. So it adds accuracy to the code, and that's why a new set of absorption coefficients is generated every time you want to change your star.
Right, okay. Thanks. That's dependent between atmosphere and stars. Good to know.
But it's easy to change the star.
Well,
so
that's
don't let
part of
the
the buyer beware
discourage you.
part of what,
Yeah.
right, what you're saying.
Yeah, we'll talk more about spectral files and those things going forward and the caveats involved with that
but
and
in a
who you
sense-
should contact.
In a sense, am I correct that actually there are two different files for stellar spectra and for
Yes.
long wave absorption? So actually, you can reuse certain files like for certain atmosphere to switch to different star just by generating only one file. I mean, not two files at the same time.
Right, the long wave radiation files carry over from each atmosphere. You don't need to change those. It's just you have a long wave spectral file and a short wave spectral file. And you just have, the long wave stays the same for each atmosphere. And the short wave file has to be switched out for each different star because of this step where there's a weighting of the stellar spectrum and the spectral interval into the new spectral file to increase accuracy.
Yeah, as I said, we'll try to go into some more detail about that because it's a very important component of the model. Yeah, I mean, for example, we use a radiation package called Socrates, which comes from the UK Met Office, and I have seen papers where people use the default Earth-specific spectral files for stars that probably they maybe should not use them with. Upon querying these people, they decided that the heating rates were not so bad that they wouldn't use them anyway. So it just often depends upon how much error you're willing to tolerate. And we have some tests that can be done to test how accurate your heating rates are. We won't have time to go in the tutorial, but we have some documentation on how to do that with the model, basically. So you can run very high spectral resolution version of the radiation code and compare it to your low resolution files to decide how far off your heating rates are for a given spectrum. Okay, we've touched on some of this now, what it cannot be used for. So we say here, variable atmospheric mass for a mix of constituents. Yes, we cannot do that with the model. You have to basically fix your atmospheric constituents and keep your atmospheric mass constant in this model. We have a beta version of the model where you can change the mass of the atmosphere for a single constituent. We've used that for Mars, as you saw on a previous slide, for a CO2-dominated atmosphere. But in general, that is not possible. And as we touched on before, super Earths, we're a bit limited there. We say here up to 10 Earth masses. I don't know that we've successfully modeled any planets up to 10 Earth masses, but we have modeled up to several Earth masses. I mentioned.
I'm sorry. Is the limit there really about the number of bars of the surface?
It's the gravity, right, and how that changes the dynamics of the atmosphere, basically. That's what we experience.
And it's also the resolution at some point. The more you increase the planet, then without increasing the resolution of the model, your grids become too big, and then several assumptions that are coming with the Earth parameterization become invalid.
Yeah, the physical size of the world will change, of course, and your grid size will change, obviously.
So that 10E is mass, not necessarily
Not radius.
I mean, it depends, but right, as far as that, the grid size goes, right, that depends on what rotation period you're doing. So it's not obvious that if there is a 10 Earth radii planet out there with a thin atmosphere rather than a big thick hydrogen envelope, let's say, so you have something in the full gap, let's say, okay, where you've got 10 Earth radii planet with a thin residual atmosphere or secondary atmosphere, right, and it's very slowly rotating so that you can have this big planet and have big grid boxes, but you still can resolve the dynamical phenomena that you want to resolve for whatever that rotation period is. It's not obvious that you couldn't use ROCKE-3D for it, but you know, as you start changing things like that by a lot, you have to at least start asking those questions. And I think from traditional terrestrial atmospheric dynamics, we kind of know what spatial resolution one can get away with for a particular, let's say, rotation period of the planet and a particular size of the planet. In fact, there have been some systematic studies of things in rotation period like that. Yohai Caspian Adam Showman did one of those a few years ago, things like that. So we have some ideas about that, but again, it's a buyer beware thing. You have to kind of be aware of the problem that you're doing and ask, well, with this model, this resolution, should I be trying this planet or should I not?
Indeed. I've already mentioned about the thin atmosphere approximation and super thick oceans. As it stands, most of the spectral files, which we'll keep touching on, are not valid above temperatures of around 400 K.
Meters, right?
Yeah, it should be 10,000 meters.
Definitely.
Funny how these typos stay in here year after
Yeah, I
year.
know. And we checked them.
Yeah, we checked it several times. Yeah, not above temperatures around 400 K for most spectral files and not below 100 K except for some Titan-specific spectral files that we have generated. So again, we will point you to the spectral files document at some point, and in that spectral files document for a given spectral file, usually we tell you what temperatures these spectral files are good for. We do have a problem with really cold planets. One thing our model does not like is when an ocean grid cell freezes to the bottom. As one of our ocean developers likes to say, our ocean doesn't like to be squeezed out of existence. That will cause a model crash, and we have some fixes to get around that. And I think we actually have a fix to this problem coming, but we've been saying that for a while now. So we have trouble doing really cold planets with this model, with oceans, if they have an ocean. If you don't have an ocean, you can be cold. It's no problem because the ocean can't be squeezed out of existence if it already doesn't exist.
Single grid cell or the whole column?
The column in the grid cell.
So when the sea ice that floats touches the bottom, the model crashes.
Yeah. Our model cannot change surface types, in essence, is what it means. There are some issues with fast spinning planets that will depend upon the grid resolution and capturing the Rossby radius of deformation. Again, that's a case of buyer beware. Be careful what you do with this model. Think a little bit before you start doing a simulation that sounds really fun. If you haven't seen us do it in the literature before, you probably should write us and ask us, does this seem like a reasonable thing to attempt with your model? We might say, yes, fine.
Yeah, can I just say maybe something about that again? You know, the second time this resolution has come up, so maybe it's worth saying that. So this is Planet 1.0 that we decided to make a 4-degree by 5-degree model because we were interested in getting started and being able to do as much as we could as quickly as possible. You increase the spatial resolution by a factor of 2 in all 3 dimensions. You increase the running time by about an order of magnitude. So nice to go to finer resolutions, but you pay a price in how much throughput you get. For the next generation of the model, which I don't know if you're going to talk about.
We are going to talk about that.
Then we are going to have a standard version of the model that will that 2 by 2.5 degree resolution, which will be better for a higher rotation rate. For Planet 1.0, we don't have that yet.
Right. I've already mentioned the business about us not being able to do mini Neptunes or gas giants, and I don't know who put this in, but I think maybe it was Tony who suggested. Remember the acronym, Resolving Orbital and Climate Keys of Earth and Extraterrestrial Environments, the key thing being terrestrial environments. There is currently, as exists in many lat-long grid models, a South Pole anomaly, which means that you have to have a land grid cell at the South Pole. You can make it the height of the ocean so that it doesn't play a large role, but it is still an issue, although I understand that this has been solved in the Earth parent model, and it's just a matter of time before we get it in our model. And as we keep saying over and over again, there are limitations in atmospheric constituents in this model in terms of the radiation and the chemistry, which we'll touch upon a little bit later with Kostas, who will review some of the chemistry things. Model version names, yeah. I mean, we don't have to go into detail here, but as I've mentioned several times now, we are the child of an Earth parent model called Model E2, and there's several versions of that. There's a CMIP-5 version, which we're basically the child of. There is currently a CMIP-6 version, which has been frozen as far as I know, and is generating CMIP results for the IPCC studies.
Code frozen, not the planet.
Sorry? Code frozen. Yeah, code is frozen, not the planet. The planet is going the opposite direction. Planet 1.0 is based upon, as I said, basically the CMIP-5 model. Planet 2.0, which we are at present balancing the model, and we have a rough draft of the Planet 2.0 description paper we're working on now, which will be a child of the Model E2.1 CMIP-6 version of the Earth parent model, plus something we call tracers, which we'll talk about a little bit later, which is basically chemistry stuff, in what will be called Model E3, which I guess will eventually become the CMIP-7 model, if I understand correctly, at some point.
No, E3 will also be a CMIP, so we're going to have two CMIP-6 models.
We'll have two CMIP-6 models,
Yeah.
supposedly.
CMIP 6 has no deadline yet, so it's a moving target.
Okay, sorry. And then we have three branches for ROCKE-3D. We also have a planet development branch. That's where all the development stuff goes on. So Planet 2.0 is a child of the planet development branch, and Planet will keep getting updates from the Earth parent model. So we're very tied to the Earth parent model because they're the 800-pound gorilla. They have all the resources, they have all the money, they have all the technology. They're the $6 million woman or man, as it were. So we have to rely upon them, and we stay very tightly tied to them, unlike, for example, the LMD model, which is basically not tied to their parent model at all. Yes, Daniel?
But so does that mean that when they do things like changing cloud parameterizations for the CMIP, that is going to trickle down into the ROCKE?
Absolutely. We have a completely new cloud parameterization scheme coming. Is that how you call it? Cloud convection scheme that Tony has been working on with several of our other cloud people here, which will show up eventually.
So E2.1, the cloud and convection are a little bit different from E2, but E3 will be a major change, and especially the cloud microphysics parameterization, something that is much more physically defensible, and I think opens up a lot of new avenues for doing interesting things for other planets too.
So there's some advantages for us staying with the Earth parent model. We have several different chemistries. Generally, ROCKE-3 runs with what we call NINT mode, which is non-interactive chemistry. Kostas will probably eventually talk a little bit about some of the interactive chemistry modes that are possible. And I think thus far, we haven't really done much with ROCKE-3D in terms of interactive chemistry.
We've done interactive aerosols with Mars, simulate some dust, but haven't published that yet. It's still a work in progress. Our Mars model is almost Mars, but not exactly.
Okay, so I think some of you have realized that we do have a code repository, and you did manage to download the model from Simplex. There is some model documentation. I would say GIS has not been great about model documentation in general. We have tried to be slightly better about documentation to the best of our abilities, but like all things, we are horsepower limited. We do have a Planet 1.0 dynamic ocean run deck, which you can take a look at, which most of you have already actually run, as far as I know. And then there is, of course, an Earth run deck with a 40-layer model, a variation of which most of you should have run by now. We have what are called the latest snapshots available for the model. So if you want to run the very latest and greatest version of the model, it is possible if you go to the snapshots directory. In general, we don't recommend running development versions of the model if you decide to download one, because things are often broken in development versions of the model. We're using it for testing, so you more or less use it at your own risk. Okay, so we have a list of GIS contacts here for people you can contact if there are different things in the model that you are curious about. Overviewing clouds would be Tony Del Genio, whose voice you've already heard. Chemistry aspects of the model, that would be Kostas Sigurias, my colleague right here. various planets, orbits, etc. That would be myself. Our radiation person for ROCKE-3D is Eric Wolf, and Eric is sitting over here. He has recently shaven, so you may not recognize him. He usually has a great beard, but he has decided that summer's here. For atmospheric composition, well, you can write any of the core people for that, including Kostas and myself. For debugging purposes, that would be Igor Ilyanov, Kostas, and myself. Try to use us sparingly. Please do your homework before you write us. Often the problems we discover are of a trivial nature. Not every time, but sometimes. Hardcore software development, of course, you will go through us, the gatekeepers, and then we might pass it on to Tom Clune, who will, as I mentioned tomorrow, will talk a little bit about the calendar and rotation rate aspects of the model. Biological aspects of the model, that would be Nancy King as the key contact person, and Nancy and Igor are experienced with the land aspects of the model. You want to change land surface type. You want to change just basically a planet that's got sandy soil and a certain amount of water in the soil. Those are the people that can help you with things like that. And the Panoply data viewer, which is developed in-house for looking at model output. Output comes in that CDF format, is Robert Schmunk. It's one of the great things I think that we have to offer is that the guy that develops the NetCDF viewer is in-house, so we can ask him to add features or fix bugs, and he's extremely fast, and he's very good. So if you have features that you discover down the road that you'd like to see, he's the person to that. Okay, thought we would go through some terminology in file system structure for the model. I think most of you have now run across this .model ERC file. Some people had troubles getting their model running because, for example, they left spaces accidentally at the end of lines in the model. That's a common problem. The model's syntax is quite strict about that. The ROCKE-3D source would be in something called Model E2, Planet 1.0, and then often there's a timestamp or date stamp associated with that, as you discovered when you downloaded your version of the model. We have a giant template rundeck directory. So the rundeck, of course, is the file that contains all the aspects of the model that make it work, including where the spectral files are, what solar installation you want to use, what kind of land surface types you want to use, what kind of ocean you want to use, all those sort of things which we'll go into. We have a large number of templates. Most of these are from the Earth parent model, and as we will probably say many times, because this model is developed by scientists, they don't ever delete anything, so the model is filled with rundecks from the past 20 years, none of which have ever been deleted, because every time you threaten to delete something, somebody says, no, don't delete that rundeck, I used that 5 years ago and I might use it again. So that causes some issues. That's why that directory is giant. So if you see a rundeck template that looks interesting, and it's not what you in this tutorial, please talk to us first before you go down a dark, empty hallway. There's this directory called the DEX directory, which you should have already been in. Oh, sorry.
Templates, I want to mention.
Yes.
I want to mention that the files which we call templates, they look like rundecs which we are using, but they are not always the same. Templates are run through CPP preprocessor in some special way. So never use templates directly from template directory. Use it as we describe in our
use the make rundeck command every time.
Yes. And give it the name. Then you will get correct rundeck.
Yeah, never copy from the rundeck directory. It's only for you to know, for the templates directory. It's only for knowing what the name of the template is, so that when you run make rundeck, you know which template name to use. Because there are also source files that will be added to the rundeck template, which you will not get if you just copy it over.
Well, there may be a lot of things be added and expanded, and it's not obvious.
Yeah, and this happens very little in Planet 1.0, but in Planet 2.0 is used extensively. So when Planet 2.0 will be released, and you will go in the templates directory and open one of those rundecks, you will see that it is very, very minimal because it has instructions on how to take things. And never copy, as Mike said, is the way to go.
Use make rundeck every time.
And
Yeah, Colby.
So is there like descriptions for each run deck, or do you just have to open it up and see exactly what's going on in it?
This is, again, one of these cases where we have extremely poor documentation. So that's why we ask you, if you don't use one of the Planet run decks, to please talk to us first, because there's no documentation in most of these run decks. And what documentation there is at the top is usually wrong, because these run decks were created from somebody else's run deck, and they never bothered to change the top of the run deck, which contains the documentation. We are hoping, I mean, not hoping, I should say, no, we're not hoping. In Planet 2.0, when we create the templates for Planet 2.0, we have actually changed the documentation, because we ourselves are guilty in the Planet 1 templates of adopting the same very scientific behavior of copying other people's outdated documentation. So the headers in the template run decks in Planet 2.0 should accurately reflect what's actually in those run decks for the Planet 2.0 run decks, right, Kostas?
Yeah.
Yes, we have made an effort to.
But still, it is very, very limited.
Yes.
So it will be like 6 lines of text saying this run deck contains those big features, and then for the fine details, you need to really see the run deck itself, and you will know what to search for after we end at the end of the second day.
Thank you. And just a word about terminology, so that people are not puzzled why we call them run decks. Actually, this name comes from the times when people were using decks of punch cards. So run deck, it's the deck of cards which you put on top of the entire deck, which basically tells the model what to do. So everything has changed, but the name still remains. That is a set of cards that you use.
This is a legacy model, if you haven't guessed it by now. Legacy of punch cards. Okay, and then of course the source code is located in the model directory. So that's where all the source code and source code subdirectories are located for the model. So if you want to learn how something works, you can look in the source code. All of the source code for your particular template run deck or your run deck will be located in there. So if there's something that you see that you're interested in, you can go dig into the code yourself, change things, whatever you like. Just buyer beware, of course. Okay, input and output locations. I think we kind of covered a bit of this already when you installed the model, where the location is defined in your GCM search path and your .model ERC. And there are relative paths in the runs deck. They do not start with slashes, as you probably have noticed in that .model ERC. User-defined input files. What I mean by that are input files that you yourself want to add to the run deck are allowed in the run deck itself. So you can put absolute path names to, for example, if you want to use a different ocean input file, for example, or a different soil input file, that is allowed to use absolute path names to your local directory. The output files are, as mentioned here, in the save disk command in the .model ERC, and they're also soft linked in the dex directory under the run name. So for a given run name, it will generate a link automatically to where you actually put the model output. So often people's model output is not located on the same disk drive that they're running the model from. For example, when we run on the supercomputers at Goddard, our dex directory is on a backed up disk, and that has a very low quota, but the model output is sitting on another disk. And so there's a symbolic link created from our dex directory with the model name to where the model output is located, which can fill up, as you might imagine, terabytes of data, which are not backed up. That's why it's called no backup, the name of that particular directory. It's a good thing to keep in mind.
And you can see that already. Since presumably all of you have run the model for the first hour. If you do an ls in your dex directory, you will see exactly this directory structure.
Yeah, you should see a symbolic link to where the output files are located. You can CD into that, and you can see the size of those files. Okay, overview of the run deck. Maybe I should have Kostas or Igor talk about this, let them drive a little bit.
Okay, I can turn on my video.
Yep.
Okay, so I have my video on.
I know, but I put you there anyway.
So the ROCKE is a really complicated thing that very few people, excluding myself, know exactly what happens in there. So it has essentially, though, a structure that makes kind of sense. So at the very beginning, there are some comments that describes what this ROCKE is doing, and then there is an object modules which says which files, source files, need to be used for the compilation of the model. So these files are Fortran files. You don't define them with an extension. The model will figure out whether it's a .f lowercase, .f uppercase, .f90. It will figure it out. And then all those files are located in the model directory. For subdirectories, they are located in the components that is the next part of the ROCKE. So you define a component, which means this is a subdirectory in the model directory with source files and its own make file. And then you do that if you have some big component that you got from someone else, for example, and you want to plug it in your model. You don't have to list everything separately. You just have it as a separate component and you compile it like this. And then there is another part that is called component options, which says to the model with which particular configuration to compile those components. So this is, in our case, it is a two-line part. And you don't have to provide component options for a new component. You can use, it might be just the default settings, but you might want to have some control from the ROCKE. So essentially the component option is when you do a make, and then you define certain options like, I don't know, F flags equals something. If you want to control that from the ROCKE, this is where it goes. Then it's a very big part of the ROCKE that is.
Well, that's not what goes into component options, if that's what you are trying to say.
Oh, it will go there.
Did you use it? Well, at least it's not intended way to use those.
Okay.
Yeah. Well. Anyway, component options is basically something that if your component can be run in different ways. For example, you want to use some CVP statements to enable different models. For example, in our vegetation model, we can run old vegetation model, or we can run new vegetation model, and we don't want it to be seen outside, but we want to be able to control it from outside. So we have just this component option saying if option equal to end or something like that, then use new vegetation model, or use different vegetation types. So that's, but for most people, unless you want to do some hacks, just leave the component options. Yeah. They are pretty much, they don't change from ROCKE to ROCKE, at least for planetary runs.
So then we have the data input files block, which contains all individual input files that the model will be using. So you know that in Fortran, you need to always define, when you want to access an input file, you need to say, open this file, and you need to provide the file name. So this is hard to do if you change input files, to go in the source code and change the source code itself. So what this part is doing is that it is linking some standard names with the actual file names you are using. So for example, you want to say, I want to use a certain file that contains the model topography. So it says topo equals a file name. So the model source code says open the file topo, and the instructions which this file is are contained in this part of the ROCKE. And you put all the input files you want in there. So you use the names that we have, or if you have to add your own input files, you can create them like this. Then there is a part that is called label and name list, which is essentially one line that says what is the run name, which we call run ID. And next to it, there is also a string that contains some comments that they will end up into the netcdf file in case you want to have it. Now, speaking about outdated documentation that people have been copying around, that comment in that run name is usually far outdated. So Then another very big block of the run deck that is called start with parameters and ends with end parameters. And it contains a lot of things that fine-tune what we ask from the model at runtime. So think of it as providing certain variables in the Fortran code that you control from the run deck itself instead of from the code. So you say you have some default values in the model. For example, you have some albedo calculation, which is, let's say we have 3 different albedo calculations, and we tag them in the model by 1, 2, and 3. And we say in the model code the default one is the number 1, but you can go say from those parameters that the albedo I want equals to the version 3, not version 1. And that informs the model that you can to use the non-default. So we have a very long list of things that you can modify from the run deck like this, and it is very easy to add your own as well. So if you want to make a simulation that you want to explore the parameter space of something, right? For example, you want to simulate a planet, and this planet has a radii from 0.5 to 1.5 Earth masses with a step of 0.1. You can, maybe no, that's not a very good example, but let's keep that as a simple thing. So you can go in the code, say that the planet mass can be taken from the run deck, and then you create 10 run decks with a different value there, and you run them, and you don't have to touch the code itself. So it's very easy to make sensitivity studies, perturb parameter ensembles, or simply modify for some reason the default values of certain key parameters. And then at the end, there is a 3-line part that is called input Z. We will go through that in detail, maybe in the next slide, soon. And then which essentially says to the model, this is when I want you to start, and this is when I want you to end. And it says a little bit more on that, but we will go through that in a later slide.
Just one thing I want to mention about run deck, which I, for some reason, is missing here. Like at the very beginning of the run deck, you will see CPP options or something like that block.
Why
and that
not the slide? No, you're right. We forgot that.
I guess I didn't put it here. So that block actually specifies CPP, preprocessing options which are used throughout the code. So you can specify your own, and it's very convenient. Sometimes you add additional code which for testing, and you don't want it normally to be enabled, but want to be able to enable it from certain run decks. So you can put that CPP preprocessing option there, and that's what will be used everywhere in the code. Though Mike will have somewhere like some include file that we have to put for that to work, but that will be later in the run deck or in the tutorial. So that's one thing to remember. Yeah. Also about the names of the files. Yes, as Kostas mentioned, you don't specify extensions, and there is some rule how make file will be searching for those. So first it will be searching for Fortran 90 files and of that type, and if it wouldn't find those, and it will be looking for like .f files. So that's also one thing to remember. And inside the components, you always specify lists explicitly of the files in the make file. So if you have to modify anything in the component, you will see that make file has explicit list of all source files. So pretty much it.
Yeah, we'll look in detail at one of these files.
So yeah, in this sounds like a lot, but we will be discussing through it thoroughly throughout the day today, and we will go through a run deck as well, I guess.
Yes.
And it will be less hidden, less complicated later on. Yeah.
We want you to understand run decks by the time we leave here. Oh, did we go?
No.
Yeah. Okay.
So for Planet 1.0, there are 3 Earth-like templates that we are supporting, and they have those cryptic names. So P stands for planet, Then there is a random number that has legacy stories behind it, so forget about it. And then it is S for Socrates radiation. M40 means medium resolution in the horizontal, so 4 by 5, and 40 layers that go up to the stratopause. And then there is a letter that I skipped in the middle, which is either absent or Q or O. So the absent means that the model has prescribed sea surface temperatures and sea ice. The Q means Q flux, ocean, and the heat fluxes are those from present-day Earth. And O means dynamic ocean. We also have a PS Mars, which is a Mars-like planet. I said that we have a Mars template, which is not exactly Mars, but it is close enough. And just see, because we are here, for planet 2.0, this list will grow substantially. So we will be supporting Earth-like planets with and without a dynamic ocean, with and without Q flux or SST fixed sea surface temperatures, with the Socrates radiation, but also with the GISS radiation. And we will also be supporting 2 different atmospheres on top of this one. So
Resolutions.
And also 2 different resolutions, both the M and the fine resolution, which is 2 by 2.5. And yeah, one thing to say is that the atmosphere of those planets is present day is pre-industrial Earth, except that it is missing 3 big things. One is has no aerosols. 2, it has no ozone. And 3, it has no water formation from methane photolysis, from methane oxidation in the stratosphere. And this is one of the 3 atmospheres we'll be supporting planet 2.
If you want those things, you can run an Earth run deck, which includes all of that stuff. You can ask us about that. Except for the Mars run deck, which does not have Earth. It's a CO2 dominated atmosphere, obviously.
Okay, so
I think
that's hands-on.
Yeah, I think we take a break here, and then I think it's a good time to take a break, and then we'll go into detail and we'll look at a specific run deck and go through everything to give you a feel for how these configuration files work, so you know what things you can change, what things you should never touch, and you can see our 4 documentation at the same time. Okay, so we reconvene in say 15 minutes. So that's 10 after the hour. And here that would be 11:10.
You guys, before taking the break, there is a question on the chat window that I am not certain I am the one to answer. Can the model's convective scheme do atmospheres where the major constituent is condensable and is condensing at some altitude, for example, CO2 clouds? So we did discuss that a bit, and I think that I guess Igor or Tony can say more about that.
So you don't want to do an atmosphere where a condensable constituent is present with other constituents in significant amounts. All right, and so you can do, let's say, a pure CO2 atmosphere. You can do an atmosphere in which water is maybe less than 10% of the mass of the atmosphere, but you don't want to be doing planets where water is, say, 50% of the atmosphere, and the atmosphere is warm. So convection is going to be creating changes in the large changes, let's say, in the mass of the atmosphere and in the local molecular weight of the atmosphere as a model. I mean, you can run the model and it'll run, right? We have to distinguish between things that cause the model to break and things that the model will be perfectly happy to run it, but will give you an incorrect answer. Okay? So this is one of the things that will give you just an incorrect answer if you try to do it.
Yeah, and I guess the question was also about CO2. CO2 condensation actually is in Planet 1 it's not enabled yet, but in Planet 2 there will be CO2 condensation, but only at the surface. So CO2 clouds are still not enabled, and we don't have condensation of CO2 through the atmosphere. But you will condense it at the surface, and as Tony mentioned, you would condense CO2 at the surface. You should make sure that your atmosphere is predominantly CO2 because you cannot change cannot change atmospheric composition interactively. So, like, yes, if you have like 50% of CO and 50% of CO2, that wouldn't work. You would be condensing it, but the model just will basically treat it incorrectly. But for Mars, it works because it's mostly CO2 atmosphere.
Daniel, you had a question?
I was just going to wonder if anything that's published in the literature, if you have those run decks also in that folder, because that might be easy for people who want to reproduce results.
Actually, we will get to that, but we are trying, any paper we have published, we are trying to put not only the crucial model output, but also the run decks for those runs. So they already exist for the most part. We don't put them in the templates directory because they're a little too specific, but they will be in, and they do exist in public repository as it stands right now.
So the template directory you should consider it as the place that you can find generic configurations that are for wide usage of people. So if it is something that you created for one paper, it is super useful, but if it is only useful for this one purpose, then it does not belong to the template directory. Because if you put it there, you have to maintain it.
Yeah, and I mean, that touches on something that I just mentioned also. If you use the model and you create a really customized run deck template that could be of interest to others, please include it in your data plan when you upload the data. Include the run deck, because you'll see these run decks are long and complicated, and it will help others use it, including the input files. So, for example, in some of our simulations, not only the run deck, but we include all of the input files we generated custom for that run. They all exist. We hope that you would do the same so that other people can take your data and reproduce it if so desired. Okay, now we've gone another 5 minutes. So we'll meet a quarter after the hour then. That's okay for everybody. Take a little break.